So, hello everyone. Today we are going to study the Chemical Engineering Thermodynamics Lecture 1. Before diving into the chapter, I would like to say this chapter belongs in second year of Chemical Engineering and it deals with the thermodynamics part 2. Because this chapter starts, previously another chapter named Thermodynamic Laws and Phases was taught in the earlier semesters. On the basis of that, we deal that you are having prior knowledge of the thermodynamics laws, but I'm gonna revise them and a recap to them. So let us see. The laws of the thermodynamics were discovered when a steam engine was to run. On the basis of the observation and the postulates, there comes an idea between the change in the energies from the work to the heat. Only this was observed, and as it was a postulate, so there were none of the contrary against it. And the basis of that, by applying the further information to it, the volumes, the temperatures and the scientific notation, a huge number of equations were derived. And there comes the development of the thermodynamic field. Usually in the thermodynamics, we deal with the interconversion between the energies that interconvert between the work and the heat. We will able to study the heat given to the system and the heat taken from the system. What happens when a particular work has been done to the system? What happens to the heat of it, and what is the resultant? Further, if we go in the chemical engineering thermodynamics, we will study the different kinds of equilibrium and we will study about the different phases in a single system. So that is a further topic. Before diving into it, I have explained you some basic introduction of the thermodynamics. So it's a little bit confusing, but if we go accordingly step by step, it might be easy for us. Myself Adnan, and I am second year student of Chemical Engineering IIT Hyderabad. So let us start. I have made the notes from the book suggested by the professor, and the author of that book is Van Hess and James Smith. This book is a foreign book and it deals with the introduction to the chemical engineering thermodynamics. So let us start. For interconversion between work and heat, first and second law of thermodynamics were prepared. That is what I said. The interconversion between the work and the energy. For example, if you are working, so let us take a basic example. In winter, you rub your hands, and by doing that, you get the heat on your palm. You rub your hand, that's the work done by you, and your palm got warm, that the heat gotten from that work. Thermodynamics help us to calculate the mathematically how much amount of work has been done, and with that how much amount of heat has been generated. That this means. The second point is, these laws are just postulate. It do not have any contrary. Like in the modern physics, we get to know the theory of Dalton was rejected. Furthermore, Dalton has said that atoms are indivisible, but that was wrong. atoms are divisible. We can separate electrons from the atoms. And furthermore, similarly, Thomson model was rejected. Why? Thomson has said that atom is just like a plum pudding, a positive charge spread throughout the body of the atom, and the negative charge is just small amount between the positive spreaded charge. But that was rejected by the Rutherford experiment, where we have seen atom is empty space and the positive part is not spread out throughout the body. Instead, it is concentrated at the center in a very very small diameter. So, but thermodynamic law do not have any contrary, because it's not a theory given by someone, but it's an observation, it's a postulate by those people who started at the mid of the 19th century. By using this, we got variety of different equation. By using this basic law, applying our knowledge of molar specific volume, molar density, some ideal gas equation, and calculus, we have derived n number of different kinds of thermodynamics equation which help us in solving the problem. So what is molar volume? Per mole. It is per mole. You know what the meaning of per mole? It means it is intensive property. It just saying the 1 mole will carry this much amount of volume. So we will consider it intensive. Do not worry, I will explain what is meant by intensive and also what is meant by extensive. The unit is its complete volume per mole, meter cube upon mole. What is the specific volume? Specific volume means the complete volume of the system per kilo. It's not the volume of the entire system. It's the volume of just 1 kilo of the system. That's the meaning of it. The unit is meter cube per kg. What is the molar density? What is mean by the molar density? It's just a reciprocal of the molar volume. It means number of kilomole per volume. That's simple. Just the reciprocal of the molar volume is the molar density. What is meant specific density? It is also a reciprocal of specific volume. What the specific volume says? It says that complete volume per kilo. And what the specific density says? It says that complete. It says that the amount of kilo per kilo of the substance per meter cube per volume. These simple basic things. And let us understand the unit conversion. Suppose there are different kinds of temperatures: Kelvin, Celsius, Rankine. So these are not same. We need to understand the conversion between them. Suppose if you want to convert the Rankine into the, suppose if you have, for example, if you have Rankine, if you have Fahrenheit, temperature in the Fahrenheit, and you want to calculate the temperature in the Rankine, so you need this conversion unit. With the help of it, you will be able to calculate different temperature. Similarly, if you have temperature in Celsius and you need to calculate the temperature in Kelvin, you can use this you can use this kind of unit conversion. Again, let us dive into the another topic of thermodynamics, that is work. What is work? Just something. Work is, we understand from the basic formula that work is the force act throughout the displacement. That is called work. We would say work is equal to force into ds, small amount of displacement and the force acting on through it. In thermodynamics, same that concept will carry in the thermodynamics, but in the different terms. Work is equal to force into the small amount of displacement, and we see pressure is equal to force upon area. So force will be equal to pressure into area. So now we can write work as force into displacement. We can also write it as pressure into area into the displacement. And now area, circular area into the displacement gives the volume. Let me show you. Suppose this is a gas and this is a piston. So this is the cross section area of it, and this is the cross sectional area of it, and it is compressed this dl. So now it is like this. So the area, this much it is compressed. This is the length and this is the cross sectional area of it. Area into cross sectional area gives you the change in the volume of it. So we can write work as force into displacement, or D, we can use L also, and we can also write it as pressure into area into dl. This gives you the volume, so we can also write it pressure into the delta change in volume. So work is a path function. For example, if I go from this point volume to this point of volume V2, I have changed the volume, and by doing that there has been a change in the pressure. There is a change in volume and change in pressure. The work has been done. Work is pressure into the volume. So the area, this area is the work done on the system or by the system, depending upon the situation. But if I go from this point, if I go isocoric, if I go from point A to point B isocoric way, and from point B to point C in isobaric way, then also the initial volume and the final volume and the initial pressure and the final pressure is same. In this example, in this graph, the work initial state and the final state were the same, and in this graph initial state and the final state are same, but work done is this much. There is states are same, initial and final states are same, but the amount of work done in the first graph is lesser and the amount of work done in the second graph is more, because we have gone through the another path. We have gone from A to B in the isocoric way, constant volume, and from B to C in the isobaric way, constant pressure. The work is decreased. So here we can conclude that work is a path function. Depending upon the path we take, work might come differently. So coming to the another thing, what is mean by intensive and extensive properties? Intensive properties are those properties which do not depend on the size of the system. For example, there is water in the bottle. I took some amount of water from that bottle and I see the density is still same. Whether I took that whole bottle and just a spoon of water, density is same everywhere, irrespective of the size. So the things which did not affect by the size or change in the size are called intensive properties. Similarly, what about the extensive property? For example, if there is 5 moles in the system, we are working upon the gas whose volume is 50 liter. I divide it into 2 parts and now the volume is 25 liter, 25 liter. What does it mean? By cutting the size, there is a change in the volume. Initially it was 50 liter and now it is 25 liter. The volume is the extensive property. Similarly,